All right, folks, good morning. I think the bugs are starting to go around. Here's some coughing and hacking. I'm not feeling great today either. And I've got a jet right after lecture is done today, so bear with me as I try and make it through this morning's lecture. I canceled this lecture on Friday because we're starting a new unit, and I wanted to start a new unit with everyone here in person because it's much more fun to do that. And then on Wednesday morning, remember I'm not going to be here. I've posted lecture 23 on D2L. You're not going to find it on the Loom website where you find everything else because I can't upload new videos or old videos to that platform. So go to D2L and watch that, and I should have access to email if you're wondering what's going on or you can't access it. Just let me know and I'll try and get that set up. Don't be confused by the lecture number. I added one lecture this year to the start of the term, and so lecture, when you look at the video, is going to say 22. It's not a repeat of today, which is lecture 22. That's just the number that was assigned to that lecture last time. So we talked a lot about tension members, probably not enough about loads on structures, generally speaking, and limit states design. But we're starting to see how the stuff that we talked about earlier on in the course starts to influence how we might pick and select or calculate the strength of tension members. Tension members are often braces. Sometimes they're hangers. If you're supporting a beam from a ceiling above, then it's not supported by a post below. Sometimes you get tension developing in those members. And so usually when we think of tension members, we think of a brace, and we focus quite heavily on tension-only members. Compression members are more prevalent, I would say. It's more common that elements are carrying compression. And so all of the columns in our building are going to be taking compression because, of course, they have to support the floors vertically, and they're aligned vertically. But if we're dealing with tension compression bracing, right, in this specific building, these braces are not intended to be tension only. They're intended to be tension and compression. So for loads to the right here, the brace on the left is going to take compression. The base on the right is going to take compression or tension. And so compression members tend to be a little bit more common for us in most of our steel structures. We're not going to spend as much time talking about compression members as we did tension members because there's not as much that can go wrong with compression members. I'm sure you remember from 2033, columns buckle, and all we have to do is stop our columns from buckling. Tension members can yield, they can fracture in a bunch of different ways. It depends if it's bolted or welded. That's less important for our compression members. Today's going to serve for just an introduction to an equation that we're going to be using a lot when calculating the strength of our compression members. Next lecture is going to be focusing on modes of buckling, how things buckle under compression. You're probably familiar with things buckling out sideways, bending, right, in terms of a weak axis or strong axis buckling, and we'll talk about what that means if you're not familiar with it. But things can also twist, and that makes things a little bit more complicated. We're also going to look at how some of the individual components of a cross-section, flange, web, can buckle locally, and that's kind of interesting and takes a little bit of time to wrap your head around. But we'll see that for the most part, as long as the plates are thick enough, we can ignore it for the most part. But if we have really thin plates, we're just going to modify the cross-sectional properties a bit to reduce the strength accordingly. And then we're going to look at columns and buildings. And so we're going to focus today on a very simple column. You probably know the effective length factor K, KL. We're going to focus on K is equal to 1 today and next day. And we're going to see situations when K is 1 and when K is not 1 towards the end of the unit on compression members. Okay? So when we're talking about compression members, we're basically looking at how things are going to buckle. And the equation we're going to be working with most is this one. And I'll talk about why this looks the way it does. It looks kind of funky, a little strange. And we're going to look at the way things can buckle. So this equation is going to give us the strength, but the strength is going to depend on how things buckle. I'm sure you've seen the Euler elastic buckling a little before, something like pi squared EI over KL squared. There's also this crazy-looking equation for torsional buckling, and I'll introduce that in the video lecture. And then we'll see how the different modes of buckling govern the strength of our columns when they buckle. And then when we talk about local buckling, we're basically just going to be focusing on how thick the plate is relative to how wide the plate is, and I'll provide some more guidance on what that means. Basically, for serviceability limit states, we're left with, well, the same stuff, right? And so it's common that we want to keep our slenderness ratio relatively low. For tension members, we looked at L over R. That had to be less than or equal to 300. For compression members, we look at KL, the effective length over R. That has to be less than or equal to 200. And basically, for the most part, if we have a ratio that's less than 200, It's going to be easier to actually install in the field. It's not going to start to bow out under very small compression forces. So we are keeping things straight. And as the effective length goes longer, we'll see today the buckling strength goes down. And so we want to make good use of our compression members, and so we want to have more strength, and so we want to avoid having really, really long and slender members because they're simply not as efficient. Okay, so we're going to talk about what all that stuff means, and today we're just looking at an introduction to some compression members. The backdrop today, this was the arrangement of the structural framing in that school on the north side. We looked at the braces that were tension only, and now we're going to focus a little bit on these columns. These columns are HSS sections 8 by 8 or 203 by 203 in metric, and we're going to look at one of these columns and how we might calculate the strength of one of those today. So again, we're looking at the compression members. We're going to focus mostly on gravity columns. You spent a lot of time on assignment 1 calculating the loads on the columns. On assignment 5, you're going to factor the loads, and you're going to pick a compression member that works for those loads. And I think assignment 5, we might also look at what happens if we were to design the bracing as tension compression bracing. What changes, what section size do you end up having, and what kinds of sections make better tension compression bracing members. If you weren't familiar with this, or I'm sure you are familiar with the Quebec Bridge, has anyone not heard about the failure of the Quebec Bridge back in the, 1800s or something like that? So a lot of people think that this was the reason for the iron ring, and the myth for a long time was that the iron came from the collapsed bridge. Basically, this was an innovative kind of bridge construction. As you can barely see up here on the photo, there is a bridge support over here where the cars drive onto the bridge, or where they should have been driving eventually. And they were building this, and it was under construction, and they were cantilevering out this big structure over a support that's down here. And as they were building this overhang, these elements down here started to bow a little bit. As you can imagine, we've got basically loads from the self-weight and from the people working on the bridge, and that's going to put a member like that into compression. And the engineer was made aware of the fact that that element was bowing. He was probably overconfident in how strong those elements really were in compression. And ultimately, once they ended up going a little bit too far this way, these elements buckled out, and the entire bridge that was under construction came crashing down and killed 84 people who were working on the bridge. Okay, so this is really important that we get our compression members right. Of course, there's been a lot of research done as to how we can design them better. And one of the things that's important in this case was a majority of the iron workers working on this particular structure were from the Iroquois First Nation in Ontario region. And a large percentage of the workers here were from that area. They were all killed, and so a significant portion of the men from that community were killed, leaving a lot of people left over at home without too much of a means to provide for themselves. So that's a solemn picture that I hope that I've painted for you. We have to get this right. Basically, after today, you should describe the influence of yielding something called initial sweep, which is just how straight the column is once it's made. Nothing can be made perfectly straight, and we'll see what that means for compression members. I'm going to talk about something called residual stress, which I introduced very briefly in lecture 2, but we'll bring it back today, and the slenderness on the behavior of real steel columns in compression. We're going to describe how the transition equation that we're going to be talking about, that first one on the first slide, fits the historical Structural Stability Research Council compression curves. I'll show you what those are and how the equation that we use fits through those and what that means. And you should be able to select the appropriate curve, or we're going to see there's an end value that we have to pick based on the kind of structural member that we're dealing with. And finally, you should be able to apply the S16 expression to calculate the compression resistance of a simple structural steel compression member. Okay, any questions about why those three things are important, or anything else that I've introduced so far before we get into the technical content for the day? Okay. So we'll take a brief review back to your 2023 class, right? Mechanics of Materials. Back in Mechanics of Materials, an equation was introduced when you talked about members that carried compression forces. And I don't think that this equation gets derived anymore from the governing differential equations. And I'm not going to do that for you either. It's not useful for us in this particular case. What is important is that if we have a column that we can model as being relatively simple, pin at the bottom, something that allows the column to move up and down at the top, but there's no rotational restraint here. There's a certain critical load P, which you might have called PCR maybe in mechanics of materials. I don't know what you called it. What did you call it in mechanics of materials, this strength? Well, I'm going to call it PE, okay? Axial load, the elastic buckling strength, PE. That is the critical load P that's going to cause our member to buckle out sideways, okay? In this equation, we're still somewhat using it today. We don't use it for design specifically, but this expression way back from the late 1700s still informs a lot of the stuff that we talk about in steel design today, which is interesting. When you were doing these kinds of calculations in 2023, you might not have seen this presented in this way before, but basically you knew that a member was carrying compression. It's possible that for really short columns, you might get the AFY strength, right? Did you do this in mechanics of materials? P is AFY. And you also calculated for members in compression the elastic buckling load, PE. And basically what you did was say, okay, well, if the member has a PE value less than the PY value, then you'd take the strength and calculate the factor of safety maybe based on that strength. Or if P was equal to AFY was bigger, then you would use that strength, right? So basically there's a point here where these two curves intersect. And so for columns where we're in this range, we're going to take the AFY value. And for columns where we're in this range to the right, we're going to take the PE value. Now, what I'm going to define, and this is a parameter that's important for us here, is lambda. And lambda is just a ratio of or a square root of a ratio. So lambda is equal to the square root of PY over PE. Okay, so these two values here. And when lambda is equal to 1, that's where AFY is equal to pi squared EI over KL squared, right? So if we define this term and we calculated PE and we calculate PY for the compression member, 1 means that they're equal. Less than 1 means that AFY is going to be less than the elastic strength. And lambda greater than 1 tells you that the elastic strength is going to be less than the yield strength, okay? So this is a parameter that we're going to use later on. Oftentimes we're going to define it as the square root of Fy over Fe, and we do that simply by dividing through this term by A and this term by A. And when we divide this term on the right-hand side by A, we get pi squared E over KL over R squared. Okay, the reason being that we're dividing everything by A, I divided by A is the radius of duration squared, and so we're going to be working a lot with the radius of duration of our different compression members in addition to the effective length. Does anyone have any questions about what these curves mean and basically what these two values represent for the column? Are there any questions about this chart before I continue on? Okay, so things that are important here. Lambda is the square root of Fy over Fe. And if we were to plot PE with lambda and AFI with lambda, this is the chart we give us. It tells us how the column's going to fail if we use some basic assumptions. The assumptions behind this equation is that deflections are small. And I'm sure you've heard, we assume small deflections before, and you can just kind of take our word for it. That's okay. We assume that the steel member has a uniform cross-section, which means I and R don't change along the length. And in this class, we're going to work with members that don't have a changing cross-section, but from time to time, structures might have tapered members where the section does change, and this equation would not be appropriate in those situations. We're going to assume that the load is applied at the centroid, or the center of the section, and we'll see when that's not okay. We're going to focus on when that is okay today, and we'll talk about when it's not okay towards the end of the course. And then the three ones that are a little bit more sketchy are that the member behaves perfectly elastically, right? So the equation itself assumes that there's no yield strength. The column's not going to yield. And we already know from this curve, it's going to yield at some point. But we're also assuming that it's perfectly elastic until all of a sudden it's perfectly plastic. The entire cross-section yields, and we're going to see that that's not an appropriate assumption. We also assume that the member is perfectly straight before it buckles, and as I've alluded to before, it's impossible to build things perfectly. Everything's going to have a slight kink in it at the start, and that's going to influence the strength of our columns. It's going to cause some bending that will increase the stresses close to the extreme fiber, and that reduces our buckling strength. And finally, we assume that the member is free from stress before the load is applied. If you paid attention in lecture 2, you'll remember that we, for some sections, have these leftover strains and stresses from the manufacturing process, and that's going to influence the compression strength of our steel members. Okay, so we're going to focus on the real behavior of compression members. Those last 3 assumptions don't always work very well for us. In fact, they're pretty bad. And we're going to see what really happens for members that can yield, that they're initially straight and that they have some initial imperfections in them in terms of stresses and initial sweep, and how that influences the strength. So we know that steel members can yield, right? So that's going to change stuff. Steel members are not perfectly straight. You just can't make anything perfectly straight, and that's going to influence the strength of the member. Sometimes the member is free from stress before the load is applied. And I talked very briefly in lecture 2 about if you have a section that's been hot rolled and you have residual stresses, if you heat it up and cool it slowly, you can relieve the stresses from the cross section. And so some members will be free from that residual stress based on the manufacturing process, though it's more expensive to use members like that, generally speaking. But sometimes this is a reasonable assumption for us when we're calculating the strength of our compression members. Okay, so what does all this stuff mean? Well, if we talk about initial strain, we already discussed in lecture 2 that if we do have a hot rolled section and we don't stress relieve it, we can get stresses near the tips of the flanges in compression that reach 30% to 50% of the yield strength. So as soon as you get to 50% of the yield strength of the column, you're going to start to yield parts of the cross section. The buckling strength depends on how strong the member is in flexure, and when you start to yield parts of the cross section, it becomes less effective in bending. And we'll see what that means for our particular column here. First, we're going to focus on sections that don't have these stresses. Okay, so if we're able to stress relieve the column, but we understand that the column can yield and it's not perfectly straight, right? Euler elastic buckling basically assumes we've got something like this. It's a perfectly straight member, but for the most part, all of our steel members, before they even start to buckle, will have some kind of initial sweep, and we usually call that small delta knot, a local geometric imperfection. Very similar to the kind of imperfections that we use notional loads to consider. When we have this initial imperfection, we're going to have more bending at the start of the problem than we do when the column's perfectly straight. When the column's perfectly straight, there is no bending. But when it buckles, it starts to bend, and when we have initial strength or initial out of straightness already present, that's going to cause our cross-section to start to yield. So if I was to draw our cross-section here, let's draw a wide flange section, something like this. In addition to this axial force or this compression force, there's also going to be a bending moment acting on that cross-section. And so if we look at the stress, if we assume a uniform stress, right, what does the uniform stress look like if we just have only axial force and no moment? What does the stress over the section look like if we just have an axial load P? It's uniform, right? It's a uniform stress. It looks something like this, right? Over the section, we've got a stress that's uniform, and we calculate it as P over A. But when we have this initial bending moment due to the initial out of straight, that's not what the stress looks like. The stress actually looks a little bit more like this, where the bending moment causes more compressive stress at the tips of the flanges, right? Something like this. The stress in the web is about the same as P over A, right? So the stress here is P over A. This stress up here is P over A plus My over I. And so the initial stress or the initial out of straight is going to cause greater stresses at the tips of the flanges. And basically it's going to yield sooner than it would if we had just a straight axial force acting on the cross-section. What that's going to do is once we reach the yield strength, maybe we start to yield this area of the cross-section, those yielded portions of the cross-section are no longer effective in resisting any stress, because when it starts to yield, we have a yield plateau, the stress doesn't increase, and we're left with what's called here an elastic core. An elastic core is the section of the member that hasn't yielded yet. And so if we think about calculating the moment of inertia, perhaps about the y-axis here, that's going to be reduced due to the fact that we have less of the section remaining in the elastic region. And what that's going to do is that's going to reduce your buckling strength. We can still think of PE as pi squared EI over KL over R squared, or sorry, pi squared EI over KL squared, but I starts to get smaller in this region where we start to have significant inelastic deformation of the column, and that compromises the strength compared to what it would be if it was perfectly straight and if it couldn't yield before it was starting to buckle. Okay, so a lot wrapped up in that, some hand waving, right? We're not getting to the detailed mechanics or theories of that, but this initial out of straight reduces our strength. When we have short columns, it's not much different. When we have really long columns, it's not much different. But when we have this range between sort of lambda is equal to 0.5 and lambda is equal to 1.5, we have what we call intermediate length columns. So this region, 0.5 to 1.5, we call that intermediate. Columns that have a lambda value longer than 1.5, we call those slender or skinny, kind of, like it's kind of floppy and it's going to buckle elastically. And in this range, we might call them stubby or stocky or simply short columns. And the lambda value that we calculate is going to tell us where in that region we are playing when it comes to calculating the strength of members in compression. Okay, we'll see how this works out later. We're not calculating the equation for this curve quite yet. We just know that the curve that actually represents the real behavior of columns that are not initially straight and that they can yield before they buckle looks something like the blue curve shown here. Are there any questions about those concepts before we continue on? Okay. If we do have these stresses present, basically, if we look at the situation back here, if we have no stresses present initially, but we have this initial out of straight, we start to reach the yield stress further at the tips of the flanges, and that reduces the effectiveness of the cross-section. And if we have those residual stresses present, basically we're going to be yielding that even sooner, right? Basically, at the tips of the flanges, we're going to be yielding this in compression even sooner due to the fact that we already have a locked-in compressive stress of up to half the yield load. And so what that means is that there's parts of the cross-section that will yield sooner when the residual stresses are present compared to if they were not present. And what that does is it reduces the effective moment of inertia of the elastic core even further, and that compromises the strength of our compression members more when those residual stresses are present. Okay, so this blue curve we're going to see in concept represents the strength of members with no residual stresses, but they have initial out of straightness, and every member has initial out of straightness. The red curve here is the blue curve plus the effects of the residual stresses, and we're going to see in this class we're basically working with these two different curves. If the column has residual stresses, we're going to be using the red curve. If we know that the column is free from residual stresses, we're going to be using the blue curve. Which of these two curves, let me rephrase this. If you didn't know if a column had residual stresses or not, which of these two curves should you probably use to be conservative and not underestimate the effects of what might be there? Blue curve, red curve. A few folks there. So the red curve is more conservative, right? And so it's going to result in a lower compressive strength. And so if we don't know if the section has residual stresses or not, we'll use the red curve. Historically speaking, what they did was they would do a whole bunch of tests and say, okay, we'll cut a section of column that has a lambda value of 0. We'll cut a section of column that has a lambda value of 0.5, and they'll do a bunch of tests, right? They'll cut a whole bunch of different columns that represent this range of the ratio lambda. They'll do the test, and then they plot the data. And here I'm plotting the actual compressive resistance divided by phi AFY, which would be, this is the yield strength, right? Yield strength of the column. And we've seen that before for tension members. Short columns have the same strength as tension members. They don't buckle, they yield. Intermediate columns have a reduced strength that are based on this curve. Longer columns have a reduced strength based on these other curves. And based on the testing, someone would say, okay, what equations work well to represent the strength of these members? And what they ended up with was 5 equations for each of the curves. And so the blue curve was represented by these 5 expressions that looked something like AFY, which is the yield strength for short columns, phi AFY times lambda to the minus 2. This is basically just the elastic buckling strength. And then there are some weird equations for the other 3 regions. And same thing for the red curve, resulting in slightly lower compressive resistances. There are these 5 equations that were basically used, and how those equations look are these sort of piecewise equations. For the red curve, for example, there's a flat portion, a curve that ends here, a curve that ends here, a curve that ends here, and then a curve that goes toward the elastic buckling region. We used these equations all the way up in Canada until 2001, and when somebody pretty smart decided he was going to come up with an expression that we could use to get rid of all these equations except one, and use that to calculate the strength of our compression members. The equation that was based on, or the equation was based on this expression. This is called the Ramberg-Osgood transition curve. And what this curve does is it transitions from a constant value, or a straight line, if we're to plot things with respect to lambda, and this blue curve down here. Okay, so for really short values of lambda, we get basically the red curve. For really big values of lambda, we get this red curve. And how quickly we move from the red constant line to the blue curve is based on the value of n that's shown here. Okay, so basically what this expression is doing is we're saying, okay, we've got y is equal to y max. Y max is the constant value. And so I might say CR over phi A Fy is equal to y max, which is 1, divided by 1 plus x naught here is where the 2 curves intersect. Okay, so that's at a value of x is equal to 1. And the value we're going to be using for x here is actually lambda, right? So we're plotting on the x-axis lambda. And so we're going to have plus 1 divided by, or sorry, x naught is the value of lambda. The function here is 1 over lambda squared. Okay, so this is 1 over lambda squared. That gets raised to the power of n, and everything there gets raised to the power of 1 over n. Now I like to spend time on this because to me it's very interesting. If we look at extreme values of n, for example, and then we look at corresponding values of y. Let's just say we're close to this intersection point here, okay? And let's just say, well, lambda is slightly less than 1. Close to 1, but very slightly less than 1. Okay, so let's just say we're just over here. And let's say we use a value of n is equal to infinity. If we have lambda just less than 1, and maybe I'll expand this expression a little bit further. We'll say that this bottom term here is 1 plus lambda squared times n to the power of 1 over n. So CR over phi AFY, which is the yield strength, so we call that the normalized compressive strength, is based on 1 over this expression here, and that's equal to 1 over, or CR over phi AFY. What if we have a small value, or a value of lambda that's close to 1? Let's just say lambda is equal to 0.999, and lambda is or n is equal to infinity. What does that mean for this expression here? If lambda is just less than 1, but n is equal to infinity, what does that expression turn into? Any ideas? So we have a value that's just less than 1, but it's raised to the power of 1 over, or infinity, basically. What happens to a number that's just less than 1 when you raise it to the infinite power? What does it trend towards? Any ideas? 0.5 times 0.5 times 0.5 forever, what does that give you? It gives you 0, right? You're taking a number less than 1, you're multiplying it forever, and you get 0. So for n is equal to infinity, and for lambda values less than 1, we get 1 over 1. This term goes to 0, to 1 over n. Anything, 1 to the power of anything is 1, and so basically we just get the value back 1. right? So for values of lambda less than 1, we get CR is equal to phi A Fy. What if we have a value of lambda that's just bigger? Let's just say lambda is equal to 1.001. What happens when we raise a number greater than 1 to an infinite power? What does it become? Well, it basically becomes infinity, right? Anything that's bigger than 1 raised to the infinite power becomes infinite. And basically what that means is that, well, lambda to the 2n is much, 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 much bigger than the 1 that's getting added. Okay, so for n is equal to infinity and lambda is greater than 1, the expression becomes 1 over lambda squared. And so we end up with CR is equal to phi A Fy divided by 1 over lambda to the 2n, all to the 1 over n. And so basically, we end up with something that's basically 1 over lambda squared, which is this curve here. So I know I lose some people in that. Basically, what I want you to take away from this is, for a value of n is equal to infinity, you either get phi A Fy or you get 1 over lambda squared. And so in this case here, the mechanics that you learned in CE 2023 are baked into the expression. But this value of n here transitions from the AFY term to the elastic buckling curve. And if we change n, we can use that to fit these different curves that I'd introduced previously. And so in the 90s, someone basically said, okay, well, if I use this equation, CR is phi A Fy divided by 1 plus lambda to the 2n all to the 1 over n, and I just change n until the difference between SSRC curve 2 and the red curve is small enough, I get a value of n is equal to 1.34. And if I do the same thing for SSRC curve 1, which is the one up here, I can get a different curve with n is equal to 2.24. And on average, it's not going to be exactly the same, but the difference is usually no more than 2% compared to the 5 equations that we used before. Okay, so we get one equation that goes from plastic yielding to elastic buckling. The value of n determines how quickly we move from the constant value to the curve. And if we calibrate values of n, we can use the same equation to get the strength for both these curves with one expression, just two different values of n. Okay, so all I want you to pick up here is there are two curves. They're well represented by this one equation. All we have to do is pick a certain value of n. Are there any questions about this equation, what it's trying to do, based on what we used to do before we continue on? Okay, so when do we use these different values of n? Well, we use different values of n when we have sections that have significant residual stresses. And in S16, sections like hot-rolled sections, hollow structural sections that are cold-formed, or some of the American standards that are cold-formed, we're going to be using the red curve. The residual stresses are significant enough that we reduce the strength compared to if there were no residual stresses. For other kinds of sections, like if we've got welded plates or sections that were cold-formed but then stress-relieved, like a class H HSS, we can confidently use SSRC curve 1, which means in S16 we pick a value of n equal to 2.24. Now again, I'll ask, if you're not sure, you see an HSS in the field and you're just like, I don't know. I don't have the drawings. I can't tell if it's stress-relieved or cold-formed, not stress-relieved. What value of n do you plug into that equation if you want to be on the safe side? Well, you want to pick the curve that has the smaller strength, which is the red curve. And the red curve is based on an n value of 1.34. So you plug in A, you calculate lambda, plug in lambda, you plug in the yield strength, and use a value of n is equal to 1.34, and you get a compressive strength back. If you're confident that there are no residual stresses, then you can use an n of 2.24 instead. Are there any questions about n and when you should use these two values? Okay, so a couple poll everywhere questions just to see how well you're picking up the things I'm putting down here. So one question is, I showed you two curves before, the straight curve and the elastic buckling curve. And true or false, it's appropriate to design a steel compression member using those two simple curves, either phi Fy or pi squared EI over KL squared. It would be acceptable to design a column using just those two curves. Excellent. I'm quite happy with this. If you're still trying to think about it, the answer here is false. And the reason it's false is because if we come back here and look at those two curves, if we had an intermediate column and we calculated the strength for design using these two curves, then we would get basically this point here. We're overestimating the strength by maybe 25 or 30% if the member has no residual stresses. We're overestimating the strength by maybe 45%, or 80%, I guess, in that case. So up to here, that's an 80% overestimation, roughly. And from here to here, that might be 40% overestimation. So we're grossly overestimating the strength of those compression members when the value of lambda is close to 1. Okay, so one more here before we do a brief example. Those two limit states I showed you, AFY, elastic buckling load, will never give a reasonable compressive resistance for a steel member. Never give reasonable values. Is the poll open? No? That's kind of annoying. Let's go see our poll everywhere here then. Okay, now it should be active. There we go. All right, so the question here is they will never, ever give reasonable compressive resistance compared to using the S16 equation. Okay, so again here the answer is false. And the reason for that is if we come back here and if we look at the AFY term, if we're using the blue curve, AFY is reasonable for really short columns. It doesn't, just because we're using this different equation doesn't mean we're never going to get a reasonable value, right? If we're over here, there's not going to be a significant difference between the S16 expression and just using the basic mechanics of materials equations to calculate the strength of the column. Likewise, out here, when we have really large values of lambda, then the elastic buckling strength gets pretty good because the point of this curve is to transition from AFY at small values of lambda to pi squared EI over KL squared for large values of lambda. Okay, so we do not design using the simple curves, the constant and the elastic buckling curve, but that doesn't mean that it's never going to give a reasonable value for the compressive resistance. Does anyone have any questions about those two concepts before we do an example? So let's look at that column that's in the school on the other side of the street, the river. We're going to be looking at this column here on the right-hand side. Okay, so over here we're looking at this one, and there's some load in the column from the floors above and a reaction at the base from the load that's acting on the column. And even though they're sort of connected to these beams, we're going to simulate this connection to the beams as if it's basically pinned, right? The connections here are intended to not develop a significant amount of bending at the ends of the members, and so we're just going to simulate that as a simple pin or a roller. And at the bottom side, it's not exactly right, but we're going to simulate the foundation as if it was just a pin with no moment resistance. We'll see at the end of the unit on compression members why we can do this reasonably. And we'll also look at situations when this is not very reasonable. We have an HSS 203 by 203. It's a G4020 Class C structural steel, 350W, though it's not said there. And so if we model it as this 4,500 millimeter long column with simple boundary conditions, roller at the top, pin at the bottom, we want to calculate the compressive resistance using the expression that we looked at today. Are there any questions about what we're trying to do in this example before we get into the calculations? Okay. So what we want to do is use the equation that we just saw. CR is phi A Fy divided by 1 plus lambda to the 2n with that stuff in the brackets raised to the power of 1 over n. Okay. So what do we have here? Well, we have phi A Fy, we've got lambda, we've got n. We need to get the area for the section. Where does the area come from? Handbook, right? The blue book, you have the cross-sectional area. We looked that up for this particular section. And so if we're looking at the cross-sectional area for this particular member, A is equal to 7,150 millimeters squared. That stuff comes from page 6-98 of the handbook, so spend some time at some point going and looking up these values for yourselves. Fy, we get that from the grade of the steel. We'll take 350W. Lambda, we need to calculate square root of Fy over Fe. And so let's try some of those things. So we're using 350W steel, which means Fy is 350 MPa. And one of the other values we need to calculate is lambda. Lambda is equal to the square root of Fy over Fe. So we've got the yield stress divided by the elastic buckling stress. We have to calculate a value of Fe, so I might do that here first. Fe, as I mentioned before, it's the average cross-sectional stress at the critical elastic buckling load. So we take pi squared EI over KL squared divided by R squared. And what that gives us, and you'll find this in the handbook, it's pi squared E over KL over R squared. This is actually pretty nice because we already saw before we need to calculate KL over R and make sure that's less than or equal to 200 to satisfy our serviceability limit states. So that's kind of helpful. We'll go ahead and calculate KL over R. We're going to use the basic modeling here. So we're going to basically assume that it's going to buckle something like this. K is equal to 1. L is equal to 4,500 millimeters. And R, well, we can either calculate as I over A, or we can look it up in the handbook. And so from the same spot here, page 6-98, we'll see that R is equal to 78.4 millimeters. And in writing that, one of the questions is, how do I pick a value of R, right? This is a square section. It's got R for one direction and one for the other. How do I know which of those R values, or which R value to take from the handbook of steel construction for that section? Well, for now, I'm just going to wave some hands and say that's the only value, because square sections have the same properties about both directions, and so they don't give you two sets. We simply get an R value. It can buckle about the strong and weak axis. It's square, and so it doesn't really matter which way it's going to buckle. We just calculate the buckling strength for either. Okay, so R is 78.4. That comes from the handbook. And if we calculate the KL over R ratio, we get 57.4. Is that an acceptable value of KL over R based on the inequality I showed you on the first slide? Well, for compression members, KL over R has to be less than or equal to 200. We've got 57.4, which is clearly less than 200. So we're satisfying serviceability with this particular column. So we can calculate FE now. We've got pi squared. E is 200 times 10 to the 3 MPa. We're not using I anymore. We're using this expression down here. Or sorry, I guess I should have divided this through by A, which is pi squared E over K over R squared. Not important. This is the equation we use to calculate FE, and that's what you'll see in the handbook. And we don't have to redo the calculation. KL over R is 57.4. And we square that when calculating FE. And that gives us an FE value of 599 MPa. Any questions about that calculation or why we did it before we continue? Okay, so we've got Fy, that's based on the strength of the steel. We've got Fe, which we calculated using the elastic buckling stress. So now we can calculate lambda. That's equal to the square root of Fy over Fe, which is the square root of 350 MPa divided by 599 MPa. And that gives us a value of lambda of 0.764. Based on that value of lambda, do we have a really short column, a really long column, an intermediate column? It's intermediate, right? Between 0.5 and 1.5 is sort of that intermediate range where the strength is significantly reduced compared to the basic elastic assumptions, right? If we look at the curve back here, we're somewhere out in this range, right? Which means we're using either the red or blue curve, and there's a pretty sizable difference between what we'd calculate using 2023 equations and what we calculate using the S16 expression for compressive resistance. Okay? Last step is CR is phi A Fy divided by 1 plus lambda to the 2n, all to the 1 over n. And the last question here is, what value of n do we select when we're doing this calculation? 1.34, which is for sections with residual stresses. 2.24, which is for sections without residual stresses. So very good for those of you who raised hands or didn't. HSS G4020 Class C is a cold-formed, non-stress relieved cross-section, which means residual stresses will be present. And if we look at slide 22 here, it includes G4020 Class C HSS sections under the list of types of sections that we use the value of 1.34 for. Okay, so we can crunch our numbers now. Pardon me, we get 0.9 times the area, which was 7150 millimeters squared, times Fy, which is 350 MPa, divided by 1 plus 0.764 to the power of 2 times 1.34, all to the 1 over 1.34. Now, if you haven't noticed this yet, you have to be very careful when you're putting this in your calculator. Brackets are important, and powers are important here. But if you get it in your calculator correctly, and remember that this is going to be a value in newtons that we divide by 1,000 to get kilonewtons, we end up with a compressive strength of 1,676 kilonewtons. Okay, so what that means is that column is a good column, first because it's meeting the serviceability limit state, as long as the factored compression force in that column is less than 1,676 kilonewtons. I didn't give a factored compression force. We didn't calculate one. The example was just to calculate the strength, and we would also need to calculate the loads to determine if the strength was adequate or not. Anyone have any questions about that example before we wrap up lecture this morning? Okay. Well, now you should be able to describe the influence of the stuff that we talked about, basically why the three assumptions behind oil elastic buckling curve are not good for real compression members. describe how the equation we use in S16, which is the transition equation, fits those curves that we used to use a long time ago. And now that we use this new expression, apply it to calculate the compressive resistance of a simple structural steel compression member. Any questions about anything we talked about this morning before we close lecture for the day? All right, just a reminder, no lab this afternoon, right? Bentley Education sent an email to everybody who I CC'd. Is there anybody here who emailed me about STAD Pro who I didn't CC? Okay, I will also CC you. I think, did you send me an email? And can you remind me of your name? Kristen? I will make sure that I'll forward that information to you so that I can help you as well. Anybody else? Okay, well, enjoy the rest of your day, and we'll see you Friday morning.